In this one, I am going to determine the number of hydrogen atoms found in 5.61 grams of magnesium hydroxide. So this one is a multi-part problem. It's going to be a little bit more involved. So let's see, let's highlight our given. So we are determining the number of hydrogen atoms found in 5.61 grams. 5.61 grams of magnesium hydroxide. And it gives us the chemical formula. So let's write that out. So our given is the mass of magnesium hydroxide, and that equals 5.61 grams MgOH2. Okay, so we have grams. We cannot go straight from grams into hydrogen atoms. Let's highlight that. So we're looking for a number of hydrogen atoms. So we can't go straight from there because our conversion factor that involves Avogadro's number, N sub A, that involves 6.02 times 10 to the 23 particles. I'm just going to shorten that to particles per mole. And there's no grams involved here. So I need to figure out a conversion factor that involves grams. So I need to connect these two using moles and grams. So basically what I'm doing is I'm using the molar mass to do that. So let's use this periodic table down here to find the molar mass of magnesium hydroxide. So magnesium is right here, 24.30. I'm going to write that down here so I can keep track of it. 24.30. I need oxygen, which is 16.00, and hydrogen, which is up here, which is 1.01. So those are my three values. I'm just gonna take those. Oh no, I'm bringing the periodic table with me. I don't want the periodic table to be brought with me. I'll just rewrite them. So our molar mass, which is denoted by capital M, with the subscript of whatever it is that we're finding the molar mass of, which is MgOH2, equals 24.3. Yep, 24.30 grams per mole, 1 mole, plus I've got 2 of these hydroxides. So I can just do 2 times 16.00 plus 1.01 grams. They're both in grams per mole, by the way. I should probably write them in, but I'm running out of space here. So that gives me, let's see, 16 plus 1.01 times 2, 34.02 plus 24.3, 58.32. And now I'm going to write definitely the units there, so grams per 1 mole. And keep in mind, this is the mass of a magnesium hydroxide formula unit or whatever. I mean, you don't refer to ionic compounds as molecules, but it's for one compound of magnesium hydroxide. So grams of magnesium hydroxide per mole of magnesium hydroxide. Okay, so the reason I'm writing in the magnesium hydroxide in this one, when I didn't do it previously up here with the water, is because I'm determining the number of hydrogen atoms. It's not asking me for the number of magnesium hydroxide particles or formula units or compounds. It's asking me specifically for hydrogen atoms. So because it's asking me for the hydrogen atoms, that means that I also need to determine how many hydrogen atoms there are in one compound of magnesium hydroxide, MgOH2. So hopefully you can see that this like 2 here tells us how many hydroxides there are, which tells us that there's also just two hydrogens per magnesium hydroxide. So that is important. So for every magnesium hydroxide, not molecule, but every magnesium hydroxide, whatever particle. So how do I want to write that? Mm, sure, we'll use N. N, we'll do N of magnesium hydroxide. No, N of hydrogen per N of magnesium hydroxide. I don't always write this as like a fraction over here. But I have one, sorry, not one, what's wrong with me? Two hydrogen atoms per 1 mg OH, uh, two particles. I'll just use particles like that. Okay, so up here, I have my Avogadro's number, and that's the particles per mole. And when we think about this right here, it's talking about the number of magnesium hydroxide particles, not hydrogen atoms. So we have Avogadro's number of magnesium hydroxide particles. So I'm going to add that in up here. So magnesium hydroxide particles per mole of magnesium hydroxide. Okay. All right, I think that this is all of our conversion factors, and I can just highlight the key stuff here. So we've got this as our conversion factor. I'm just highlighting them because some of them got a little messy because of the molar mass. That's our final molar mass, and then this is our conversion factor here. The unknown for this question is the number of hydrogen atoms. So N of hydrogen atoms equals question mark H atoms. And before you say, hang on, but isn't it just two? Well, no, because it's two hydrogen atoms for every one particle. And we don't have just one particle, we have 5.6 grams. We don't even know how many moles we have yet. So we have to do a lot of calculations here. So I'm hoping I have enough space. I don't think I do. So I'm just going to move some stuff around. Let's move this up to the top. Move this up to the top as well. And let's move our periodic. Let's actually delete the periodic table for now. We don't need it. So let's do our calculations down here. So I'm looking for, starting off my unknown, my number of hydrogen atoms equals. Again, we start off with whatever value does not have a fraction associated with it, so it doesn't have like this line. So that would be the magnesium, or sorry, the mass of magnesium that we're given. So 5.61 grams. 5.61 grams mg OH2. And I might just write that in kind of closer, maybe a little smaller, just so I don't run out of space. Just so I know what it is that I'm talking about. Okay, first conversion, we want to involve grams. Where do we see grams in our conversions? So let's just check this one off. We've used that. This one is particles per mole, so no, not using that. This one, okay, so now we've got grams per mole, so that's a possibility. This one over here, no grams per anything. So we're using the molar mass first. So we want to make it so that we're canceling out that grams. So we want the grams here to be in the denominator, just like we did previously. So let's get the grams in the denominator, which means that moles will be in the numerator. Moles of MgOH2. And it's 1 mole of MgOH2. And 58.32 goes in the denominator. 58.32 grams of MgOH. So now we are canceling grams with grams, and what's left over on top is number of moles. Is that what we're looking for? No, not yet. So now we need to do another conversion. So let's move this over so we have a little more space. Another conversion, and we need it to involve moles this time. Moles of magnesium hydroxide. So let's see. So we have this one here, which has moles of magnesium hydroxide in it. We've already used this conversion factor right here, so let's just check this one off. We don't need to use it again. And then over here we have atoms and particles. So no, not this one. So we have to use this value right here. So Avogadro's number. So we have a fraction. We want the moles of magnesium hydroxide to be in the denominator because we want it to cancel with this numerator right here. And let's see. This is our fraction, so we just continue with, there's like a 1 right here, right? It's per mole or per 1 mole, it's the same thing. Per 1 mole magnesium hydroxide, and it's 6.02 times 10 to the 23 particles of magnesium hydroxide. MgOH2 particles. Okay, so we've used that one now. And let's see, does this cancel moles, moles? Good. And make sure that it's the right type of moles. So it's moles of magnesium hydroxide, moles of magnesium hydroxide. So it's the moles of the correct thing. So that is going to cancel with that. And we're going to be left on top with particles of magnesium hydroxide. Now we have this as our last conversion factor. And we have atoms in the numerator and particles in the denominator. So let's see what we need. We've got we want particles to be in the denominator because we need it to cancel out with this particles right here. So let's write that in. Particles of MgOH. Particles MgOH. And let's see, that's 2 hydrogen atoms. Sorry, my mouse is messing up. 2 hydrogen atoms per 1 mole. Or sorry, per 1 particle. So this is our numerator, the 2 hydrogen atoms per 1 particle of magnesium hydroxide. So is that going to cancel? Look here. So particles magnesium hydroxide, particles magnesium hydroxide. Great. That's exactly what we want. We want it to be on the top and the bottom. And now we're left with hydrogen atoms. So is that what we're looking for? The number of hydrogen atoms? Let's look. All the way over here? Yes, that's great. That is exactly what we're looking for. So we want to be left with atoms of hydrogen in the numerator. So now let's plug this whole line into the calculator. Again, I could plug in those ones, each of those ones, but they are just gonna, it's not gonna mean anything. If you divide by 1, if you multiply by 1, it's just the original number. So I'm not going to put the ones into my calculator. Anything that's on the denominator needs to be divided by, and anything that's in the numerator is multiplied by this original number. So it's 5.61 divided by 58.32. So 5.61 divided by, and I probably should go into scientific my scientific calculator, scientific mode. 5.61 divided by 58.32, okay, times, so I've done this one, I've done this one. Now I'm multiplying by this numerator. So times 6.02, this function right here, the EE, that's scientific notation. So 6.02 times 10 to the power of 23. What's the last part over here? Okay, so times, oh, sorry. Times, so let's maybe enter this so I don't, I'm not super familiar with this calculator. Times 2 hydrogen atoms gives us 1.15. Let's see, 1.158 times 10 to the power of 23. Let's move that away. Hydrogen atoms. So I'm using whatever unit is left behind in the numerator. So hydrogen atoms. And let's round that to the correct number of significant digits. Up here, I was given 5.61, so that's 3 sig digs. And that's our lowest number of significant digits. So we're going to round this number down here, our answer, to 3 significant digits. So we're going to end at that 5. So the 8 is bigger than 5, so we're going to round the 5 up to 6. So 1.16 times 10 to the 23. Careful you don't drop the 23. I've seen people do it before. That's important to keep in there. 1.16 times 10 to the 23 hydrogen atoms. Okay, I hope these videos helped. Let me know if you have any questions.